All right, I think everything is in order. Good evening and good whatever for whoever is watching on YouTube. Is it really working? Is it really working? I guess it is. Okay, I'll assume it's working. So, tonight I want to keep working on our little VM. And so we have this landing page here. All right, so there are a couple of links to the Twitch page, to the GitHub project, to the YouTube channel, and so we are working on this virtual machine for evaluating a simple mathematical function on a lot of values at the same time. So something which is very easy to make into a parallel function that will make good use of the vector architecture of our CPUs, whether they are Intel or wrong camera, whether they are Intel or ARM8. The point tonight is, as what we are implementing is actually an interpreter, there is a big, so you have this loop around the list of instruction, and you will read an instruction, you will decode the instruction, and once it's decoded, you need to go to the bit of code that actually implement that instruction. And that's really something that you can find in every single interpreter on the planet. And our goal tonight is to make sure that it's not too bad or too badly implemented. When I say that, I mean I want it to be relatively efficient, and I want it to be relatively robust to changes in the instruction set. Meaning, we have this list of instruction which is encoded in a Rust file, activations.rs, I think it's there. Yes, so we have this list, yes, download. We have this list of instruction, actually it's not that one, it's this one now, which are used as the communication between the Rust world and the assembly world. And so we need to decode the carob, and according, depending on its value, if it's 0 we are done, if it's 1 it's move, if it's 2 it's a load, etc, etc. But I want to be able to add something in there without having to go and fix the assembly. So that's another requirement of what I want to do tonight if we manage it. So basically I will make something that will parse this list and create the jump table for me in the assembly file. One of the reasons for that is the three main architecture for Tract are ARM8, ARM7, and Intel. So it's three of them. And maintaining this list of operators and the assembly implementation by hand is, well, I'm just too lazy for that. So we'll do it by scripting and stuff. It's not something new, it's something that I already did in this very project, because there is another similar architecture in the matrix multiplication. And it's smaller in terms of operators, if I remember correctly. No, it's not that smaller, but that's this bit. And we have this jump to comment, which are actually, I mean, they just, the label which follow them is the label that we will use in the assembly file where we want to jump. So we will do the same thing. But before that, we will do it by hand once, just to see how this works. So let's look at our assembly file. And it's the one with act. Yep. Okay. So for now, the jump table is here. So we have implemented only two operations. The first one is done, which is code 0. And so if we are done, we are just going to end of inner loop here. And basically, we are moving to the next slice of values and starting from the beginning. If we hit number 14, then we have a max with constant, and then we go to this bit of code to run this operand on the registers which have already been loaded. But if we compare this to activations, so this must match these. So 14, it's max const. I added some numbers because, as a matter of fact, this is so cumbersome to do by hand that last time one of the bugs was I had counting the instruction wrong. So this is a good sign that we can't rely on this being done correctly by hand. And if I mean, in this case, you can see that our switch case, because it's actually a switch case, which we already have implemented actually, because we have this implementation of more or less the same logic in Rust for the platform that do not support, I mean, for which we wouldn't have an assembly implementation, or for also for reference and to compare our the assembly implementation with something that we know works and which we can easily instrument. So basically, the bit is this. This is the star is fetching, and I mean, all of this is kind of decoding the instruction, so it would be equivalent to our load here and this, and that just keep the first 2 bytes, which are the opcode. And it's 2 bytes because here we have this U16 representation that tells Rust that these things, this enumeration starts with a 2 bytes discriminant and then contains the payload. And then we have this, which is the equivalent of the switch case, except we just have done and max const. Max const, which is implemented by this and that. If we want to do everything by hand, if we want to do it by hand, we can have perfectly good, perfectly valid implementation like this. W71, and for now I will use BEC unsupported because this instruction is not supported. That's the move, and we haven't. I mean, we have implemented just max const. So for now, move is not implemented, and we have showed that would look like this. Etc. etc. 1, 2, 3, 4. Okay, and the problem with this is I will stop there because it's boring as hell. If we do this, for instance, when we are hitting max const, we will do all of these comparison and jumps before finding one that works and jumping to max const. And the max const is so simple actually, because it doesn't do any memory access, it just do local stuff in registers. So doing this will take more time than actually executing the max const. I mean, same order of, it will be in the same order. So we want something better, and so there is a trick. There is a trick which consists of manipulating directly the instruction pointer. So once again, as it's something that we already have done in another part of the code, we'll go and have a look. I think it's in the dispatcher. So yeah, that's it. So we have the same kind of thing. So we have this loop, which is the interpreter loop. And here we are loading, in x2, we are loading the next instruction opcode. And the jump happens here. So this we'll ignore for now because it's, I mean, actually, I think it should go away because this is just checking that the value in x2 is between 0 and the right, I mean the limit of the jump table, the size of the jump table. And I mean, it should be the case. We are in unsafe territory and we want performance. So doing this check it's a bit over the top, I think. I mean, in the case, the code that we are looking at right now is the matrix multiplication, and each of the actual operation will take quite a lot of time to process. So it's kind of okay to keep these because the cost of jumping stuff will not be that bad compared to what is actually done in the actual operators. But in our case, we will just ditch it because we won't check it because it's too expensive. We'll go very, very unsafe. Basically, we are trusting the Rust code to do the right thing and not messing up. All right. So let me check here. Okay. So as you can see, also the jump table is not explicitly written here. There is these weird templating things, and so this is related to the jump2 labels that we've seen in the other code. So ultimately, that's what we are going to have in our code. But let's see how it works. So the point is, it uses these BR instruction, and we are going to look at the ARM instruction set. Should I open my big PDF right away? I really don't like the website. So branch to register. Branching continually to an address in a register with a hint that this is not a subroutine return. Okay, that's exactly what we want. So what we are doing here is we are computing the address where we want to jump by looking into grabbing the address of this label, which is labeling the first variant of the switch case, the first case, and we are adding to it the x2 offset to the left by 2. So what does it mean? X2 is the opcode where we want to go, and we are shifting it of 2. This is logical shift left by 2. So basically we are multiplying by 4 because each of these jump instructions that are generated in the loop are coded over 4 instructions. So by doing this, we are just jumping to one of these jumps, which in turn send us to the right place. So let's see how it works. So I need a label, jump table. I'm not sure why it does this. And I noticed he did the same here, so I don't know. We are going to put a lot of B unsupported. So the first one is actually supported because the first one is done. So that's this guy, end of inner loop, and I will just rename it done. Then we have a bunch of unsupported, and we must get to 14 to get the max const. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then max const. Okay. Now, our address is in W6, which is Xsys viewed as a 32-bit register. And so we can just, we need a register to do the computation. So what should I use? What should I use? Something that we haven't used yet. So x0, 1 and 2 are used for the parameters. x3 might be free. No, x3 is used here. What is x3? x3, oh yes, we're loading the next constant. So I can use x4, I think. Yeah, x4 seems to be unused. So in x4, I will extract the address of jump table. Yeah, I don't know what it does this. And then I will add to x4 x7 with the same shift to the left by 2. So here I computed one of these address, and the last thing I need to do is to jump to this address, brx4. And that should do it. Let's have a look. The one which is working is relu. And so that's the generic case, which is the generic case is a Rust implementation. So no big surprise, it does work because we are not testing anything. Nope, I'm going to use my Raspberry Pi 4. Bit of suspense. Hope the Pi is working. I haven't checked. It is working. And what test should pass? Because we have leaky and threshold relu which are failing, which is okay because this one uses operator which we haven't implemented yet. But relu is fine, so I guess relu that was a generic one. So when I pointed, but that is the one we just changed. If we want to make sure that we are really testing something that does something, now it should fail. Suspense again. And yes, now value is failing. So I mean, it's a good hint that our code is actually doing something and doing it right. So next we're moving to the generation of these from, and we will use the same trick. We will add some annotations in the Rust code, parse them before generating the assembly, and using them in the assembly through the templating trick. So src activations, src frame activations .rs, and we have this kernel ops. So I'm going to add jump to comment down tab doesn't work in this situation. Jump to move. Jump to, can I speed this up somehow? Jump to load. Jump to, yep. I'm not sure how I can speed it up, so at least I'm going somewhere. Receipt. Let's try. This one should be easy to do faster. Up, up, jump to, up, no. Yes, so add sub mul min max. Okay, a bit of cleanup, same trick. Jump to, add const, subconst with multiple typo, mul const, in const, max const, fma. So I'm going to keep this comment, but I'm going to add jump to fma. Nearly there. Jump to if pause then else, I guess swap bc, swap bc, jump to floor, whew, jump to po of int. Okay, so we're done, except we're not done. Now what I need is I will need all of these labels to be present in the assembly file. So a bit more of VI voodoo. Let's keep these. Up, up. So I already had down and max const, and all of these I will put them at the end for now, or should I keep them in order? Yeah, I will keep them in order. Up, so max const is after min, but all of these need to end with column. Can I do this? No, okay, it's fine. I need to jump to unsupported for now for all of these. Okay, we have a couple more to do. And this one for now are not supported. And that's it. So, now the question is, I want to script the jump table. So let's have a look at how it was done for the other case. So here I have this jump table. So I'm parsing the other Rust file, extracting a line that contains jump2. I mean, it's very simple. Just split up to jump2 and make a list of string that I will go and pass to the MMM various matrix multiplication assembly kernel. So I'm gonna define a second one. I think, yeah, so I'm going to put Rust file here. I guess this should be enough. Yes, let's see what it's called, jump table. Here we go. So we will have a bit of a problem here because we need a second one, and this one is called jump table. So it should be called jump table for matrix multiplication. We will call this one jump table act for activations, and we need to parse activations. And I will not rename the other one because, I mean, not at least not on stream because it's too boring. Can I do this here? I think so. And here I can use Rust file. Okay. And now I should be able to do the same thing as in the other dispatcher. So the dispatcher is ARM64 SIMD dispatcher. And that's it. And this goes away. Okay. So wrong jump table. The new name is jump table act. And that should be it actually. So we should see just leaky relu and threshold relu in error, and relu should work. Pom 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 pom. Not too bad. Not too shabby. Okay, let's commit this because it's already, yeah, some kind of achievement. Oops, there is a bit of dirty. So it's in .rs, and it's on the FMA line. There is some spacing. Yep. Okay, it's gone. And something I need to do, I think, is if I reformat the file. Yeah, so I don't want this. So I'm going to add the magic annotation that I spotted in the other one, frame multiplication fuse, to prevent Rust format to change anything here. Okay. Okay. All right. Okay. Well, that's it. I mean, that's. I thought it would take more time actually. So if I'm going back to my issues, that would be this one. And so what's next? What's next if I follow this roadmap? Is this guy? But I think I'm going to do this one before. Why? Because it will be so much easier to implement that one if you have this one operational. So let's do this. So what does it mean? It means our test should be one-liner. So if some of you were there last week, you may have noticed that I have a lot of redundant code in the testing of these operators. So, for instance, here, so I'm calling this macro for each and every external implementation. So for each external assembly implementation of a kernel, and it calls in turn this act tests macro, which is in activations tests, and this will generate multiple tests. So we first have this prop act unit macro that is actually here, and this macro does a lot of complicated things, including creating an aligned tensor because the kernel expects align data aligned on this value. So the kernel is, of course, the assembly function. We are filling it, and I'm not happy also with what we are testing because we are filling it with one single value. So expected, that's terrible. Expected is we are treating. So yes, we're taking this tensor as a slice, then we iterate on it, we clone it, and we are applying the refer meaning reference function to it, and the refer function is passed through there. But I mean, all of these, I mean, these generate a vector of the same lane as a tensor of the single value x once it goes through the function we're implementing. So it's not a great test. Here we are finally calling the implementation that we want to test, and this is not calling it, it's implementing it. I mean, no, it's not implementing it, it's calling so it assumes that we have a function that provides the macro code program for the function, and that it has to live in this place, which is, so they are here for nop and max const, and we're translating it from the intermediate form to the kernel form, and finally we're running the program that we have obtained on this slice that contains whatever number is the same value duplicated. This just wrap that vector in a tensor, and we are using a tracked close enough function to check that we are indeed close to the value we are expecting, because there can be, we need to account for some subtle rounding errors. Okay, and then we have this, which is the same thing all over again. Max const big alpha. So this is a concrete test where we are implementing. So yeah, this is really terrible. So this is a prop test. So it's going to try to find some x and alpha value that will fail. And the problem with this, yes, and these guys are concrete tests. So first, I think I can make a function that will contain all of these. But even that, I wouldn't be happy. I have several problems with this. So first problem is I need one way to run the prop test. So that's this line. But I need concrete fixed named tests for failing example. The workflow is I'm using prop tests that will try to find x and alpha values that crash this test. And once prop test has found an issue, I want to make the test concrete in the code to make sure that it has a name and that it will be run again all the time. So that's the first thing. So we have the prop test is here, and here we go again. We have this thing which is the same as that one with one subtle difference, which is 0 here or 0 there. Okay, so I want to factorize this code. Plus, I want x to be non-uniform. I want prop test to be able to try any value in any position. The reason is, if for instance, let's say I have a max function that takes a, b, c, d, and so it should return max of a and alpha, max of b and alpha, etc. And if I'm using the same value for a, b, c, and d, which is what I'm currently doing, if for instance the code is broken in a way that does this, I will not see it. So I don't like the way I don't like that here we are making a uniform tensor, so we will change that. Okay. And assuming that we have a vector and so there is also this repetition factor. because I'm careful about the first. It's not a repetition factor. It's the number of slices that we will process. If you remember what I said last week, our kernel will work on a fixed number value, like the one that we worked just a few minutes before is 32n, so it will work on 32 value at a time, and then it will move to the 32 next, and then 32 next. And the repeat here, so here we are forcing our test sample to be 32 times, so NR is our 32, and we are forcing it to be 32 time repeat, where repeat is 1, 2, or 3, to make sure that we are not only testing the first pass over the loop, but also the second and the third, to make sure. So all in all, I think we should make a function, or maybe not a function actually, because the other option is an object, and I'm starting to think that it might be a better option. Let's go with function first. So this function will contain, first we will try to get this and at least factorize the code over this. Let's see if we manage that. This is a run kernel test. It will have to take TI. So that's the type of the element in the slice. And we have some constraint on that. Plus the kernel, which has to be activation kernel working on TI. Okay. And this function will take, instead of taking nothing, it will take its input as a slice of TI. And I think that should do it. So this guy goes away. So the repeat will have to be dealt with separately. And yeah, so what stays is we still have to do the alignment. So we will do the alignment in there, because that bit is a bit tricky to do. So what it means is we are locating 0 aligned of size input, input.len, input.len, 0 aligned, that's the shape, and this is going to be k aligned. Then once I've done this, so this is a tensor of TI. Once I have this, I will copy input in my input tensor. Tensor as slice mut ti dot unwrap assign copy from, maybe copy from slice input. Okay. So expected is expected. So okay, so I need to find a way to provide the reference function. So the reference function will be a function of ti that returns ti, and let's make this a trait because it will be easier. So here I'm going to call refer of x. So expected becomes a vector of ti. And what's wrong? Yes. Input, so we're going to use, I mean, we could use input directly actually. Okay. Next, I'm gonna make this tensor, track tensor. Finally, I can run, so I need the program. And the program will be activation program. What was it? Program? Yes, program TI. So I can prog is prog dot translate, and I can call krun input. So it's no longer input because I need to work on my tensor, which is aligned different. Input is not. Okay. And finally, I'm going to compare expected with tensor. All right. So that's the function that. Let's see if we manage to use it. So run kernel test. We need the input. Okay, first problem, the input which I don't like. But we will do a vector of 0 with k, which is actually, because we're in a macro here, so that's it. Then we need the program. So the program is, and we're in a macro, the program is max const of 0. So 0 again, problem because it has to be ti 0. And the reference implementation will be x with x of max and ti 0. So there's a bit of a problem here, and I can probably get rid of this. So what's wrong? Yes, so here I will probably need to use, so here I'm in macro, so I need to do this and create, or else it doesn't work. And it's frame activations tests run kernel test. And resolve import. Why? Why oh why? There is no typo. Create frame activation. Yes, that's where I am. And resolve import. No run kernel test mode. Module test is private. And if I do this, no. Okay, the same. Can I? So the problem is this macro will be used in a very different context. So I need to point in a kind of absolute way to this place. So the module cannot be, if I'm using function, the module cannot be private, but it's fine because it's only compiled in test, so we don't care. And actually it's public. It's not test, it's tests with an S. Okay, and now run kernel test will have to be made public, I guess. Okay. So what else? Max const. So this function takes 0 argument. One argument was supplied. Max const takes 0 argument. Really? So max const is this dude, and it has one argument. So I guess it's not picking the right one. So we are at the same place. I mean, run kernel and these function are at the same place. So I can probably use a star here. Okay. TI0, that's just more. I need to use num traits 0. Yes. What's next? Expected. Okay, so that's fine. Max const. The return type of this call is f32 due to the type of the argument pass. Arguments of the function are incorrect. So the function is over there, and refer was an implementation of a function. So max const returns a program of t, and this guy, except I'm going to use that instead. It won't fix the problem. So what's wrong here? Expected reference ampersand. Okay, here you go. Expected integer from f32 max const. Max const takes a t and returns a program of t. So what's wrong here? Should I do I need to say that I want max const of ti? Expected it's because of this one. So this one should be also ti. It starts to become awesome. Still not happy. Activation f32 is implemented for S activation. To S activation is a Rust function, the generic implementation in Rust. Cannot satisfy. Is it a problem of? Yes, I need to force types again. Yes. Okay. All right. I am happy with this. Semi-happy, I would say. Because if I want to do now, so that one was the same with a max count of s dot this huge value and x of 0. So I should be able to do this. Also up, tap. So x is 0. That's good. And so const alpha is that's good. Cut it. I think that the LA datum type is assumed to be convertible to from F32. So let's see what we get. Cargo test. So this is going to test on the Intel machine the generic implementation. And it fails. Yes, because I need to, yeah, because of this. Okay, so it's still not exactly a one-liner, but we are closer. And so I'm still not happy with having to repeat this stuff. So what I'm going to do is I'm going to do a module, one more. That I will call, I will put it there, prop test. Up, and that way I can put all of these in the module for everybody. And nope. Okay, so I've broken, what I've broken? Argument are now incorrect. What's wrong now? Expected max const of 0. So what? This function takes 0 generic argument but 1 generic argument. So we have a confusion about what is a max const function. Let me check, because I think these guys are maybe defining it. Yes, it's back. Cannot find type S activation, that's the only error. Yes. So where does it happen? It happened in SRC generic activations. Okay. Cannot find the activation in this scope. Come on. So what if I move this here? Matter of fact. Oh, it was already there. So we need to check if act tests expects char to be a type. So if it's a type, then it shouldn't matter where the test is included, because if it was an identifier, we would need to have it locally, but as it's a type, it comes with its pass. So that should be alright. Cannot find type S activation in this scope. Okay. And is there a bit more information? So could it be one of these? Yeah, okay. Nope, still there. So indeed, what else do we have? I mean, we are entering here. We no longer have this macro, so it's one of these two. I mean, or the two actually. Let's try like this. Okay, so now it's compiling at least. So why? What is happening? So somehow here we are not finding char, which is a type, so that's super weird. Because there shouldn't be any problem. I try to similar name exist, of course. Cannot find type. Let's comment this line. Okay, so now it's working again, so it's really a problem on this line. And so it's with S activation, so that's char. But the weird thing is, I can't figure out why it cannot find the type in this scope, given that it's a type. So I mean, it should be resolved as a type on the call site and then just be forwarded here in the macro as a type. And so we shouldn't have this kind of problem. I have a workaround this which I don't like very much. Maybe, which is to, instead of using ty, using path. And then on the call site of the macro, which is in generic, src activation, no, it's in src generic activation. Here I can use crate actually, activations, so generic. Is it any better? It is better. So yeah, there is definitely something I don't understand. Let's see if I can still make the other. So first, the second function shouldn't be a problem. And then we need to check if it works for the assembly kernels. Okay. Alright, so I will need to use the full name, but that's, I mean, if it works like that, I'm okay with it. It will be a bit long, but I can live with this. So it's act amp. Oh yeah. So we have one more to fix. src frame. It's very frustrating. I mean, macros. Act ample. So here the kernel is a function, so it's an ident, and it has to be yes, it has to say an ident here because it has to stay an ident, or else I will not be able to compose it like that, like this, if I make it a type. So can I? No, that won't work either. This is getting messy. This is getting messy. This is not nice. I don't want to go there. I mean, it was fine with the type, really. So same problem here. Not finding scope. So it tells me that I should import it. So let's see, because actually the it is, I mean, in the context of, because we have two contexts which are different. The assembly context and the Rust context are a bit different, but so let's look at the ARM64 at the SRC frame activation act ampl. So in this case, the type is func here, and the test macro is called here. And actually I should do this, and this guy will already put prop test. So this, the responsibility of this one is to yes. So I have a first module with the definition of the function. Then I have the func, which is actually the type, and then I have this module. But if I'm doing this, I guess. And here, so this macro will substitute by this. So if I use super like this, I guess I will be able to propagate. Yes. So I have a variant that works for both, and it tells me that this super is unused, but it's because it doesn't compile any assembly. So I'm going to allow unused import on this guy just to get rid of the error. Okay, so we have something that kind of works. It's not super nice, but it will do. So the trait 0 I can move away, I think. And now my objective was to get tests to be one-liner, and well, it's not perfect because it's very dirty one-liner and very long lines. Plus I'm in macro, so I don't have auto format. I kind of need to do it myself, but I mean, it's acceptable compared to, it's better than what we had. What did I fail to? No, it's okay. And same here, I'll do the same formatting by hand. Here we go. So we have the input, the expected output, in the program and how to compute the expected output. Okay, so this is not, it's not great, but it's acceptable. Now I want to have a closer look to this guy, because this one, I mean, we're going to use it for two things. First, we need to test the elementary operations. So each operation, okay, so it's crashed already. Okay, so we need to test. I mean, I need to test max const, min const, max, min, sub, add, all of them separately, and I also need to test. I mean, integration, so relu, leaky relu, etc., with a sequence of operations. And the question is, should I use the same? I think so, actually. I think I should use the same function. The question is, should this be a macro, or should I just write the prop test here? Let's see, now that I have this function, so if I want to do a prop test on max const, for instance, it would be map const prop, and so I need to call prop test around it, because prop test, this macro extends what? Oh, come on. I need some imports. No. Prop test is ambiguous. Okay. Expected expression. Expected expression. What? Prop test bang. That's wrong. Glob import, and oh, it's because of super here, maybe. Oh, I call it prop test. Right. Okay, activation tests. Okay, better. So now, okay, I still have this one. Expected expression from keyword fn, expected expression row c. So the thing is, when you do a prop test, it should be something like that for x in, let's say something simple for now. So, okay, first the macro which was lost. Okay, and now the question is, if I want to test max const, I need alpha in really any TI. So that's some prop testing. Should I use, not here, but there, use prop test prelude. Okay, and I want to test with x. So x should be a vector. So this vector is a prop-test thing that allow to define an arbitrary vector. I mean the weight a generator through an arbitrary vector. And so in this vector, the element will be any ti. and the number of elements should be let's say that for starters it's going to be char and l. Let's see if this works. And I think I need to make it just like this. Expected type function vec, so it's x in vec require the bound, so I think that's, let's see, the trait that just use size range, so it doesn't like this, so I'm going to use another syntax. And we're going to have to try and make this better, because so the thing is, this thing is made to okay, so here we are, that's good, it does work. And so now we do a max const of alpha, and that's a vector, so it's x. This function, yeah, like this. Okay, and is it a one-liner? It is a one-liner, a long one-liner. So I guess if we manage to factorize this and may also make it dependent on the size, I mean on the repeat, I guess it's acceptable. Yeah, I think it's acceptable. Okay. So this will replace that. So let me erase it. So that's and it will also I suspect it will also replace this one. Let's see. Okay, so to make this a bit more easy, I want this to be separate. So let's say we'll call it input strat. Strat means strategy. That's how this is how in prop test you call the way that you define a random input. So in our case, what we want is a vector that is made of elements which are any element ti, and so the first, I mean, this works in that it generates a vector of exactly nr elements, but it's not what I want. So first let me try and fix this function, this strategy function. So I will use a box, or I can do maybe imp strategy. Yeah, let's try this one. Strategy of oh, just nothing. Okay. Extract. Strat. Ah! My fingers. Okay. So do we have a problem here? The size of cannot be known at completion time within. Whoa. Okay, let's see the first error here. And hopefully it will be easier to read. Okay, the thread prop test strategy is not implemented for fn item fn.amp strategy. Yes, I mean, that's a very stupid mistake. Okay. Now. So yes, I need to specify that the item, which is called value, should be an array of ti. Nope. Yeah, I think I need to say that this is a vector of ti, not an array. Better. Yes, it's happy. So the last thing that I don't like here, my tiling. No, my tiling, it's not i3. So somebody is asking me about working at Sonos. So welcome. No, it's actually not i3. It's macOS. It's very. I'm a lazy guy, so I like macOS. But I'm working remotely on a Linux computer. If I recommend working at Sonos, yes, I recommend working at Sonos. But I won't. I don't want to. I don't want to speak too much about Sonos, even if I actually have more in corporate stuff. I don't want to talk too much about it on the stream. Please ping me any other way if you want to get more insights. Anyway, back to business. Back to business. So that's where we are. That's where we were. Yep. So yeah, I wasn't happy with that bit because here I'm generating a vector of exactly NR elements. And what we said before is testing for NR is fine, but if there is a bug that only appears at the second loop or the third loop, then I will miss it. So I need to call the kernel with number of elements which is a multiple of its natural operating size. But I want this to be 1 time, 2 times, or 3 times this natural size. But that's pretty easy to do with prop tests because it's a prop flat map, and it was called repeat. So I will get this name again, and blue, and the size of the vector will be just. So I'm in macro, so I need to format my end. Let size equals char nr times repeat. Nope, that one is required. And here I'm going to use size plus 1. So I suspect there is an easier way to do that in prop tests, but I just never found it. So repeat as you size. Yeah. Oh, I will actually make 1 to 4 u size. Here we go. Here we go. So I have my extract. I have my. It's not too bad. Merci. Thank you. It's not too bad. Meaning if I want to do min, it's just copy. copy pasting this, and so it will be a bit repetitive, but it's tractable. Actually here, and this is wrong, it should be alpha. Well, I mean, it should find an error. Let's see if it works. Because we are using alpha, and here we are using 0 for the reference implementation, so there is no way this should work. And I could test it locally actually, because this code is activated on both the assembly case and the Rust case. And it didn't run any test. Okay. That's a lot of tests, but yes, okay, it's good. It tells us that our test doesn't work. And we know why, so let's just go and fix. And I'm going for change. And because it's faster, we'll test on the Linux platform with the Rust kernel. You can see that on, oops, cannot see anything really. Blue, 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 blue. I was saying something uninteresting, so forget it. Okay. Right. So now, I mean, the next step. The next step is so yeah. So this function here was doing the same. I mean, it was calling the kernel directly, because there is something else, but I think we have. That's the problem of doing stuff 1 bit every week. I forget stuff. So that's what we are looking at. We don't have much test coverage for whatever happens in the function above that wraps, but this function is shared with other parts of the framework, so I guess we can just be happy with these local tests. So let's do a bit of cleanup. Heroes testing no-op. Can I, should I test no-op again? Why not, after all? So a no-op function would be let's test no-op, and we don't need any alpha, we just pick x, and we are going to do so these are actually, I mean, yeah, they're actually a callback to this function, but I'm thinking that maybe we should try to make it easier. Like for instance, I mean, a program is just a vector of operators. So here, if I'm doing this, I'm going to accept activation ops of ti. And if I'm doing this, here I just need to wrap this in a program. And maybe I should actually build something more usable, but that will come later. Today we want to focus into the test and hopefully do a bit more assembly. So if I'm doing this, I mean, I can do the no-op in line like this. that's no op, so x gives x. Okay, so this one will be a max const op, max const of alpha. Failed to resolve op, so I need to import that. Could even, maybe I should actually do this, because that way it's even easier. Hey, I mean, it won't be a one-liner because we have the if cond that must stay, but it's getting kind of nicer. So here the program is max const with ti 0. Come on now, what's wrong? Provide the argument vector. What? Did I mess up with the parentheses or something like that? Why is it not happy? Expected slice from struct programs. That's the other guy. This function takes 3 arguments, but 2 arguments. So usually this means that, yeah, okay. All right, and this one will just be that. Okay. It is kind of better. Because, yeah, I like it better actually. So max const is done and no op is done. So this it's still a bit messy because there is the macro aspect of it, which is a bit but great colors. Bertrand Guy. Oh Bertrand, salut Bertrand. Thank you. And now I'll be self-conscious because anyway, so so what are the next steps really? We have done we have done max const and we have example for max const. What are these supposed to do? So if I want to make this work again, yeah, absolutely. If I want to make this work again, so yeah, so that's a macro. I've already discarded it. But can I piggyback on? Can I piggyback on this or do it by? Yeah. Yeah, it should be nicer really. So what I'm going to do is I'm going to use this as an example, and so I'm doing relu. So I just need next, and the test will be and the question is what should I put here, and I guess I should use macro, so create frame activations definitions. relu. And I think it was a function. Pom pom pom. So we've seen this one before, and it's a macro being confused, yes. And that argument is functional incorrect. Yes, because now I have a program and I should have just a vector of operators, a slice of operators. What I can do is, well, I mean, it's actually pretty easy because it's just this. Yes. And it's max of ti in 0. So formatting by hand again, because I'm formatting by hand because I'm in macro and the auto format is not working. Missing some brackets, and that would work for relu. It's a bit crowded in there. So relu is here, and we have not, we have max const of 0, we have max const prop. So this should be called relu prop. I'm using the suffix prop when it's prop test. So let's try and stick to this. And so I'm putting the, so I'm putting prop as a suffix when it's a prop test. And I'm putting some kind of useful name when it's a manual test with a fixed value. Okay, so I guess now that we have this, and it's so much nicer than what we had before. Can I get rid of this? One less warning maybe. And I still have the warning about act ample, but that's because on Intel I'm not generating any assembly kernel for now. So this code doesn't activate. Let's try to get rid of the warning while we're there. So act amp is here. So I want to allow unused macro. No more warning. The tests are passing. Okay. So there is still, why do I have this act nope and then act test? There is still something a bit off. So act test is starting there, going there. So I have another act nope somewhere. Where is it? Generic activations. Oh, okay, so it's a test. It's a local test for generic, so it's not a test that is. So this test. The point of all of this macro is that this test will be shared between all of the assembly implementation and the Rust implementation too. Whereas this one has been defined in generic activation, so it's just testing the Rust generic implementation. Okay, so I think I'm more or less happy with this for now. So I'm going to commit better test expression. But it hasn't been 2 hours, so I think I'm going to keep working a bit, and let's try. Now that we have all of this, doing the missing bits should be relatively easy. So, for instance, I'm going to write the test. Yeah, so for instance, let's say we're going to do affine. So, we're going to do affine prop. So affine has an alpha and a beta. It has two parameters that I must provide, but it's pretty easy. Same for beta. And so affine is, come on, stop shouting like that. I guess it's, I forgot. Let me check. So SRC frame, I mean, actually we can look at our notes from before. So we have this is the issue. So affine is alpha x plus beta. Super complicated. Alpha x plus beta. Just what the hell is wrong with yeah. That's the problem with working in macros. Everything gets, I mean, everything stupid becomes complicated. So it should fail because affine will use it will use what? It will use mul const and add const, and it didn't fail, which is a problem. Oh yeah, but yeah, on the it didn't fail because we just tested the generic Rust implementation, and this one has everything implemented. But if I move to the Raspberry Pi, I will need the assembly, the ARM64 assembly implementation to work, and we should fail because we need mul const and add const for affine. So we are going to see it fail, and we are going to just implement what is missing. And before implementing what is missing, we will actually implement a local test for mul and add. Okay, so we have failures, but that was expected. And it's affine prop. Okay, that's perfect. So now affine, why did it fail? Because it failed because we need mul const prop. So same expression except it's mul. So there is one more opportunity to do some very dirty things with macros here, because this one, that one, and add, which I'm going to add right now, are the same thing with very little difference. So there could be a macro, but too much macros is really not, yeah, it's too much. Okay. So now we should see the three failures, one for affine, one for add const, one for mul const. running, and 3 hours. Affine at const mul const. Perfect. 64, 64 CMD, 64 blah, 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 activation, and so add const and mul const. So what we need to do is we need to, I mean, same thing as for the max. We add preloaded the constant, the actual constant in W3. So we are inserting it into one of the 3 vector elements. And we are also moving the interpreter instruction pointer 1 slot away, because we actually used a constant. So the next value is not the next operator, it's a constant associated with add const. So we need to skip a second slot to fall into the next operation. And I think that the f_add function can work with a single value, which is not the case of fmax. I think I can write this. Whereas for fmax, I had to duplicate the value into all the slots, all the lanes of v24, and then use a full v24 with the other arguments. But I think that, if I remember correctly, the operator set is a bit inconsistent here, in that for add and mul, if I remember correctly, this variant exists while it doesn't for min and max. 5, 6, and 7, and same 1, 2, 3, 4, 5, 6, and 7. Operand 3 must be a SIMD vector register. Okay, so I was wrong. I was wrong about that, so it's fine. We will just, no problem. We can fix it very easily. And we're duplicating the value onto the 4 lines of v24. And I think our add will work. Here we go. And yes, the add is working. And let's do mul. So we should have everything green. No, I've seen red. Okay, so what's wrong? Oh, I missed the substitution. What did I do? What did I do? Here we go, and all green. Perfect. Should we do one more? Should we do one more? Should we do one more? So we could do art sigmoid should already work. Let's try it. So affine hard what? Art sigmoid. Oh, this one has disappeared. I guess frame activations, definitions. So leaky, affine, leaky, soft sign, art switch. Yeah, art sigmoid disappeared. So we'll put it back. Min max, so it's an affine. It's an affine function plus constrained by 0 and 1. So we're going to start from affine, and in order it was after threshold relu and before soft sign, right? Yeah, art sigmoid. Okay. So art sigmoid. So min const 1, so 1, so the same problem. 1 and max const 0. And let's relu affine art sigmoid. So I'm going to use the function I just defined, art sigmoid, and the function is min of this with 1, ti 1, and I'm taking max of this and ti 0, and yeah, okay. Nope. Ah. Okay, let's do it the other way around. So x plus alpha, x times alpha plus beta dot minimum with 1 dot max with 0. So once again with 0 and with 1. Nope. So I need the trait 1 to be present. num trade 0, and I also want 1. Okay. We're going to test locally. And let's make it compile first before going too fast. Okay, I want to concentrate on the Raspberry Pi. So what else do we have? We have a soft sine with a t, x over 1 plus apps. Let's do this one. And hard switch would work also, actually. Yeah, hard switch. Hard switch should work out of the box. Hard switch. Hard switch. So hard switch has fixed parameters, and that's hard switch, and hard switch is, I think I did, yeah, actually, I mean, oh yes, with F32. Okay, so they're not usable. So the problem with hard switch is, but yeah, I think, yeah, we can use the same trick here, because there is this, in hard switch we have a half value and we have a one fixed value, but we are going to use this trick. So it's max, okay, oh yeah, so no, this one will not work out of the box, but that's fine. So we have alpha, so this is actually the same thing as hard sigmoid, because it's a mean, it's alpha x plus beta, and we're doing a mean with 1 and a max with 0, so that's the same thing as here. The only difference is once we've done that, we multiply by x, and alpha is 0.5 and beta is 1 over 6. Really? Activations, definitions. Hard sigmoid, hard soft sine, hard switch without the underscore. I'm not sure which one I prefer. Yeah, so to define fix, and there was also this trick which is not super nice. So it should fail because we have in our switch we have this mul. Oh, and we have a move too. Wow, a lot of stuff to do. So it should actually fail more abruptly. No, it shouldn't fail like that at all. So is my function wrong here? Yeah, it's alpha. Alpha is 1/6 and beta is 1/2. All right. So I've mixed up the two constants. Plus, nope, not here. What? Something weird is happening with my connection, I guess. Again? Come on. Oh, the caps here. Okay, so it's not failing anymore. If I move to the Raspberry Pi, it should fail. And it should fail because we need move and we need mul. So let's do the move test. So the move instruction takes 2 registers. So we will need a way to pick a register to be able to build an arbitrary instruction. That's fine. I mean, I will define arbitrary for register ID. So arbitrary is the prop test trait that tells prop test how to register an arbitrary register ID. Need to import it. Yes. And arbitrary width. That's the name of the function that I need to implement. So it doesn't have any parameter. So tip is a bit weird because we need to. We can have arbitrary stuff with parameters. So parameters. In my case, there is none. And the strategy will be a boxed strategy of register ID because that's easier than anything else. And so it will be, there is a macro to do that. It will be either just A or B. Or guess what? C. And that is a strategy, and I need to box it so that, that's just because you don't have to define the type here. Cannot find function struct just. Okay. Prop one off is not defined. Let's go propo test, the composer prop test. Come on now. What? Okay, so I did all kind of weird stuff over there. Use prop test. I guess that's one more of these cases where prop test is there. What's wrong? The test. Yes, I guess I should only go to the test when I have tests. I have a bit of deja vu feeling here, so I'm not sure if we didn't try that already last time. And with the interaction of the macros, yeah, that's it, act test. But maybe we will do it differently this time. And the act test here, we are in config test, so it shouldn't be a problem. Back in macro hell. Oh, so there is test and tests. Yes. Okay. So we're getting somewhere. Now prop test is found. It's just boxed. And that's just a matter of one more import, I guess. boxed. Box strategy is included now. There is a prelude. Okay, that's nice. So now we have our arbitrary function to generate random registers, and we can do the prop test for move. Let's do it. So it's going to be move prop, and we will have a source register, which will be any register ID, and we'll have a destination, which can be any register ID. Okay, and we will run a move from SRC to DST, and here we can see that we have a bit of a problem, because how to test this? Yes, we won't be able to test it like that, because it's not observable actually from the outside. So if we want to test this, what should we do? We should put something in B and try to move it to A, but the way to put something in B is not that easy, unless we implement a load and test load before we test move. And even there, I mean, if we do load, see frame activations. So if we do load register and T, yeah, that one could work. Okay. So we'll delay a bit that one. And we'll start by doing, and we're going to load to A, because we don't really, I mean, we can try to load to someplace else, but it's not super observable. Load, so we can do load A prop, and that means that we will load X, and this time X is not a vector, but it's value, because loads a constant over the entire register. So X in any TI. And here, so what we are going to do here is, if I load something to A, to the A register, which is the register which is used for input and outputs, I should observe the value, but that's, I'm not sure I can do much more in terms of testing. X, and I should see X. What's wrong now? Yeah, I still need, oh yeah, so I still need the vector actually, because I will put the vector, and instead I should see just the single value that I'm loading. So I still need this. So I'm going to call X as usual, and this one will be constant. So I'm loading the constant, and I should observe the constant. because I'm loading in A. And this guy needs to be imported, but I'm in macro, so nothing works. It's fine. Okay, so let's test this one at least on the on Intel. Well, it should work because everything is implemented. Okay. Another test I can devise is I can test that if I'm loading something to B, then I should see X, and same for C, because loading to B should not affect B and should not affect, and same loading to C should not affect A. Load B prop, and that's load C prop. Can I do something else in terms of testing load? As long as I don't have the move or any operator that use B and C, that's about it. But we can start with this. So let's go to the Raspberry Pi, and it should fail. And I will try to limit the output. And let's see. Nope. So how to decode load? First, we need to know which register will be impacted, and so artsigmoid failing. Why is it failing, artsigmoid? Okay, later. Let's focus on load. Load should load. So we need to figure out which register we need to write, and actually it will be 3. We will repeat the same thing with the 3 register. So I think we are going to do another little jump table, because what's going to happen is first we need to extract the third byte in W6. So let's do this. We will do a right shift, a logical shift right of, and we will do it into W7, W6 by 16 bits. And we are going to mask this with W7 0xFF. So this way we should extract 1, 0, or 2. And then we are going to left shift. We are going to, okay, so load jump table. We are going to do jump to load A, load B, and load C. And here I must, so I can reuse X4 again, so I'm going to extract in W in X4, I'm going to extract load jump table, and I'm adding to this, so into X4, I'm adding X7 left shift twice. So these are my 3 instructions. Also, I need to offset 1 slot more the instruction stream, because we have a constant following the operator. So I can do that first, actually. And so I can jump to X4. So I'm jumping to one of these 3 guys, and load A will be it will be, so something I can do in all the case is I can, well, no point. Yes, point. So here I know that I have loaded the second, the constant is in W3. So I can insert this W3 in my free in my V24 free register, and so now I just need to do fmove V24 for S. It's actually a dup, because I will copy in, so I'm doing load A. So I'm dumping into V0 for S, I'm dumping V24 S0. And I'm doing this for 1, 2, 3, 4, 5, 6, 7 registers. 1, 2, 3, 4, 5, 6, and 7. And after this, I can jump back to the beginning of the instruction loop. So that was load A. Load B will be similar, except we are moving stuff to 8, 9, 10, 11, 12, 13, 14, 15, and load C, same stuff, but to 16, 17, 18, 19, 20, 21, 22, and 23, stopping just before our main VIC24 register. Jumping then to inner loop, and yeah, let's try it. Pum pum pum. So I'm still trying to understand why. Oh, maybe because B is an instruction. Okay, so you can see that our tests on load are working. Should we do the move one? Because the move ones, it's similar, except there are 6 of them. Should we do them right now? What time is it? Okay, let's do the moves. It's gonna be a bit repetitive, but I guess we can do that. So yes, so activation / tests. So I guess for the move, what we can do is we can load something to A, load something to B, load something to C, then move. How can we test this? It's not super easy. We can do something similar, like B to A. Let's do something like that. So I'm going just to do the same than before. So I'm picking any x vector. I'm picking constant ti, and I'm going to move to load the constant into B. Then I'm going to move. So I'm not sure which one is destination and which one is register. I assume that I did like that to be consistent with the assembly order, but I'm not 100% sure. And so if I'm doing this, what I should observe as a result is I should just see const, because this will load the constant in B, and this will overwrite A by B. Okay, so move. The problem with move is we have six different implementations. I mean, six different operators. So how to and I mean the encoding is a bit of a mess, because we are going to have they're going to be stored into two different register IDs. I mean, we can find a move A to A, which doesn't make sense. So one way to do this would be to say that we implement the move in two steps. So first step is we move the origin register to our V24 to V31 values, and then we implement the second part. So we're moving stuff twice. It's don't like it very much, actually. I want this to be relatively efficient. So if I want to do it another way, then I will need another jump table, and it's even more complicated, because in that case I mean, I need to compute. I mean, if I do a jump table, I will have it means I will have move A to B, move A from B, and move BA, and move C to A, and move A to C, and move B from C, and move C from B. And the problem with this is if I look at the values in the two register IDs, I will have 0, 1, 1 0. A and C will be, yeah, so it's a proper mess. A and C will be 0 2 2 0. B and C will be yeah, 1 2 and 2 1. So this one needs 2 bits. This one also needs 2 bits. So I could do that. Let's try to do it. So we are going to, we have 6 values, and they are all defined. It's six possible values among 16, because 16. Yeah. So that one, if I spell them in binary now, that one is 1 0, this one is 0 1, and that one is 1 0 0 1 0 0 1 0 0 0 1 0 0 1. So I need 4 bits. So 4 bits. There are 16 possible values, except only these 6 are correct. So if I'm sorting them, then I guess we have this. And so if we do move trump table, then we are going to have B, which is the move A to A 0 0. So this is an op. So we are going to jump back to inner loop. That's A to A. There is something that doesn't work. Oh yeah, because there are even more which are invalid. All right. So then we have this value, which is one that actually exists. So it's move A from B. Then we have move A from C. Then we have move then we are jumping one. We are jumping 1 1. So 1 1 is unsupported because it's an invalid move. Because 1 1 would be a D register that doesn't exist. So that would be A from D. Then we are back to something that exists because we have move. So this one is down. This one is down. 1 2 3 4. Yeah, move B from A. Then we have an unsupported one. Then we have move B from C. Yeah, that's BB. So BB is actually supported, it's just nope. So we are jumping back to inner loop. After that, move BC is done, and BC was that. So we have an unsupported, which would be B from D. Okay, after B4D we have move C from A and C from B, and then we have more stuff that doesn't exist, but we will have to put it there anyway. So we have we have C from C, then we have C from D, which doesn't exist, and we have the 4, 3, 4, which do not exist. So that's our jump table, and to compute the offset in the jump table, we need, this time we will have to, it will be a bit more complicated. So we are going to left shift W71 and do this. So we are extracting the third byte, plus now we need to extract the next one, the third one. So we're going to do this in place in W6, and so now I have two values, one in W7 and one in W6, and I must shift left W6 by 4 by 2, and I must, so actually what I should do is I should add to W7, I should add W6 offset left SL LSL by 2. Okay. So W7 is first reg. No, first reg should be dest, unless I did everything the other way around, which I haven't checked yet. So that's W6 is SRC, and that way I'm making 4 bits destination source, and I can finally extract the address and jump. So I'm going to extract move jump table address like this, and I'm adding x7 offset to the left 2 times, and that should do the jump table. But now we need to do the actual implementations, and it's a lot of work, and it's hard to test these bits because of well, because it's not observable. So I don't like that very much. I will have to think about it, because I don't like it at all. Anyway, move A to B. So we are going to move fmove. So B is A is V0 dot for S, and I'm moving from V8 dot for S. Okay, 1, 2, 3, 4, 5, 6, and 7. Oops. Same here. 9, 10, 11, 12, 13, 14, 15. And after that, we jump back to inner loop. So that's the first one. From C. So same, except it's 16, 17, 18, etc., etc. Then we start again with B. So move B from A. Okay, one at a time. So that one I should be able to do something like that. Not too bad. Okay, so that's move B to A, and we have move B from C. B from C. So I will get rid of these and pick these instead. Okay. Then finally we have move C from A. So let's pick this one. So I can fix this, get rid of these. I have C here. Commas. And finally, the same the other way around. A from C. Did it already, so now it's C from B, the last one. C from B. So I'm not changing C, but B, I have it here in right position. Okay, let's see. Top, oui, aïe. All of them are wrong. What did I do wrong? X error top half of the 128-bit SIMD is expected as operand 1. So fortunately I get all of them wrong. So let me check what how I do moves in. There shouldn't be that many actually move. So that's a move in X register. So yep, no, not that many moves in in F in vector register. So let's have a look at this. I don't like this website, but so we are looking for advanced CMD. And we are looking for moves. Anything that look like a move vector element to scalar. No, this is not it. That's the dup. So we're moving one scalar to vector. Nope, that's not. Is it something that doesn't exist and has to be implemented by a clever alias? I wouldn't be surprised. These are conversions. move neg. Okay. So there is one way to implement this, because obviously the move is not there. So what they do not, it's not there because there are one or more trivial ways to implement move with operators that do something. So to save one opcode, they decided not to include the move. We could use fmax because max of a and a is a. So we could say that instead of here we can so let's try this. I'm going to say that fmove are replaced by fmax, and I'm maxing the source vector twice, I mean with itself, and writing the result in the in the destination vector. So that's one way to implement a move, and min and max are really cheap, so it's fine. It's just that we need to fix all of them. Up. Okay. Here we go. Okay. So this is move C from B actually. Let's test on the Raspberry Pi. That's something where Stack Overflow could tell us if we've missed something obvious. So we're looking for ARC64 advanced SIMD move vector register to another. Oh, damn, what is vector addition? Nope. Okay, advanced move vector register. Google is often better at looking into Stack Overflow than Stack Overflow itself. So advanced SIMD register move and floating point register transfer instruction. So vdub vmove arm core register to scalar, scalar to core, between core and single precision, between two arm core register and two single precision register, between two arm core and double wall, blah blah blah. So okay, so it is assumed that you will guess, you will find yourself a way to to move between the SIMD registers. Advanced SIMD copy, move general purpose registers. So that's the same thing, I guess. And actually there is another, there is even another way. It's to look for the, because these are advanced CMD, but there are also this one, floating point instructions, and f move. So here floating point move to or from general purpose. Okay, that's not the same. It's from the general purpose registers. This has to be the load and store, yeah. And prefetch. Okay, so that's interaction with memory. Okay, so I guess, I mean, there are other operations. I mean, I did a fmax, but also could work and or a bit to bit and an or. They should work too. So we have a problem here. Move B to A doesn't work. Okay, so is it move B to A, or is it move B to A? So that should use this one. So V0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yes, 8, 9, 10, 11, 12, 13, 14, 15, okay. So let's see if I'm running just this one. So minimum failing input, const equals 0. So what is the test doing? The test is doing, that's because maybe it's the test which is wrong actually. Move B to A. So I'm loading the constant in B, then I'm moving B to E, assuming, let's check the order of registers, because so if I look at one of the definitions, one which has a move, so here I'm moving A into B because we are at the beginning, and at the beginning only A is worth something known, so a move is destination source in that order, so that's fine. So here I'm loading to B, and then I'm moving B to A, so I should observe const. And what I can see is wanted approximate blah blah, minimum failing input, so it's an X which is not fully empty with a const of 0, so we should see 0, and we're not seeing 0. Okay. I'm still a bit surprised. Could it be because the value here is extreme? So I'm wondering if maybe I should use some more robust operators. I mean, because all floating point operations do some weird stuff with nans and stuff like that. They are magic value. So instead of doing floating point, it's probably better if I find something like or and on these vector registers which exist. It's just a matter of finding them. Advanced CMD, logical and compare, shift, general. So shift of 0 would work. Shift of 0 would work, but These are using, but it's okay. It's just so. I mean, there is this weird thing where they're mixed up two instruction sets. So there is the instruction sets where the registers are indexed. I mean, it's V0, V1, etc. And there is this other. There is this. Okay, so it's because sorry, I'm confusing. And because I'm confused, because I'm looking at the 32-bit instruction set. That's not what I want. Advanced SIMD vector instructions. So I'm looking for and yes, that would work. That would work because whatever is in the second register is what I want copied into the first one. And the T is an arrangement specifier. It can be either 8B or 16B. So we can work on either 8 bytes, which is half of the vector, or 16 bytes, which is the entire vector. So that will work. And it's called end, just end. Okay. Let's try this instead. So I'm replacing fmax by end. And on the same selection, I'm replacing 4s by 16b. And I need to do that several times. Okay, I'm still failing. And same kind of mix-up. We have a problem here. Just 1, 2, 3, 4. One vector for the end. It's the same position, which I don't know if it is significant or not. Let's just check that the load. So we're loading to B. 8, 9, 10, 11, 12, 13, 14, 15. Oh, that's correct. Should we debug? What time is it? Session is already nearly 3 hours long. I think we will keep that one for debugging next time. And then we can move on and finish implementing all of the first block. So the first block is these ones. So yeah, I think we are going to stop there. And so next time I can check this one today, and next time I can probably check that one instead. Okay, so that's it for tonight. Thanks for watching, and well, just see you next week.